Hello everyone and welcome to We Meet at Digital Days. My name is Marie-Therese Kohl and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is Automotive Introduction of New Products. Our speaker is Loran Völkel. He will hold the presentation and will answer your questions. Before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions via microphone during the presentations. Nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. You will find the chat function in the webinar control panel. This presentation will be about 15 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are 5 minutes in addition scheduled for this. If we are unable to answer all your questions within this time, we will answer them via email afterwards. If you still have any other questions left, just mail us at exhibitions@we-online.com. We will try to answer all questions promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our event. You will receive the link to the presentation in the next few days. Also, the recording will be available at our website shortly. But now, I would hand over to our speaker, Laurent, and I wish you an exciting presentation.
Hello, everybody. I hope you can see my screen. Please, Marie, if you can confirm, I will be happy to know if it's
Yes,
working. Okay,
we
great.
can see Laurent.
So, hi, everybody. My name is Lauren Völkel. I'm field application engineer at Würth Elektronik, working over 20 years in this beautiful company. Today, I want to introduce to you in a short way some new products which we did develop special for automotive application. First of all, if you think about automotive cars and application, you think, why special product? Well, for automotive components, there are different requirements. There are several different tests to be done. First of all, you can imagine that if you make something for automotive, you have to do this production parts approval process called PPAP. You need to be on the database, this International Material Data System, IMDS. Many OEMs ask for IATF 6949, so this is the International Automotive Task Force, which is the new release since 2017 after TS 6949. And of course, all the components which have been produced for automotive devices or application, it must be tested according to the Automotive Electronic Council. Because we're making these passive components, we test them for AEC-Q 200. You may ask also sometimes why we use so different materials. The most used material for ferrites are like nickel zinc, of course, and we start to use also magnesium zinc for EMI, but we have some different components also done with manganesic zinc and also nanocrystalline cores. You can see in this graph, it depends on your frequency. You can decide which core you can use for different EMI application. If you have a problem like in lower frequency, less than 1 megahertz, and you want still to use the nickel zinc material, it's not so good. Maybe you have to make a lot of turns, and this is in automotive production process is very difficult to make by hand a lot of turns, and because of that we decide to introduce also here some new cores like manganesic zinc and also nanocrystalline core. The difference between nickel zinc and manganesic zinc is that first of all, they need to be coated. The surface is conductive, and because of this reason, you need a coating to not make any short circuit, or the dust from the core don't make any short circuit on the PCB and so on. They can be used up to 150 degrees Celsius. You can apply it to the wiring, to the harness, and low frequency is quite a good solution. Another new component is this IENA, which is made from nanocrystalline cores. In the past, was only just few companies that I know, two of those who made that nanocrystalline cores, but the license for this patent is due, and now everybody can make nanocrystalline cores. Nanocrystalline cores is a little bit different from the sintered ferrite because this is not a sintered material. Here we don't just not coat them because they are pressure sensitive. In this reason, we put them in a plastic enclosure. So the ferrite, in this case, the magnetic material, I can say like that, it is not only just coated, it's in a special plastic enclosure. And because of that, you have operating temperature up to 125 degrees. The nice comparison with the sintered ferrite is that the nanocrystalline core are not temperature dependent. Sintered ferrite, they have a drifting in the temperature, but because this is a kind of iron melted and very high temperature, then cool down, it's a little bit different, and that's is not so temperature dependent like the sintered ferrite. What's happened in the ferrite, in fact, when you're applying some EMI energy? In physics, we have this first law, I will say, energy never get lost. Energy must be always transformed in another form. So actually, you have two vectors. You have the electric field vector, the magnetic field vector, and these both vector make with this magnetizing, demagnetizing the core, generating kind of movement, border domain move are moving in the ferrite, and that's energy. And in fact, we say ferrite transfer the EMI noise energy into heat. But even if you take, I will say, something like um, Fluke camera, thermal camera, and you look to the ferrite, you won't see that to getting hot really. In immunity test by Automotive could happen at 400 volts per meter if the cable wires are very long and you make exactly the resonant point with the ferrite, you can done that the ferrite gets hot. But if the ferrite start to be really such hot that you cannot touch it, this is not anymore EMI, this is safety problem, and you have to carry on that. You can see here a comparison by a DC-DC converter, which have been done with 2 megahertz switching frequency, and we choose a 10 microhenry inductance unshielded and make some without put any EMI measurements levels, just record the peak level of this DC-DC converter, and then take a soldering iron, desolder the unshielded version of inductor, and take a shielded version of this inductant, also 10 microhenry, just to see what is happening if we change just the inductance in the EMI for a DC-DC converter. And you can see now that changing this inductance from unshielded to shielded one, we have 90 dBm better reference on the EMI. So just because of conductor emission, unshielded version can contaminate the system with his magnetic field. It's very simple if you use a shielded version. In an anechoic chamber by radiated emission, I think the pictures speak by themselves. If you use an unshielded version, you will have more radiated emission instead of using better version, which is a little bit more cost, maybe a few cents, but the shielded version is that what I recommend to be used for this DC converter storage inductance. And these are the most popular are this PDA or also the PD series. The difference between PDA and PD series is just because you have here a junction where the wire can be used on the uh, a base like a plastic base, or you can use metal base. And the metal base this time have the advantage that you can put multiple wires, so twisted pair wire or multi-wire, and you can solder them. By the plastic base, we don't using soldering, we use welding. So you can use only one wire. You have a perfect couplerity, much better DC resistance. That's the big difference between the PD series and the PDA. By the PD, we can go up to 2.2 millihenry. By the PDA, we only buy 1 millihenry. But I like much more the MAIA, the MAIA inductor. This is a new technology where first we make the winding on by air choke, and then we take some iron powder and press the iron powder together with this winding in one tooling together, and it means have the best magnetic shielding and extremely low DC resistance. They don't need a plastic socket or something like a base, and they don't need to be soldered, so on. So they are very, very highly reliable, even up to 150 degrees Celsius, the high temperature version. And you can see here how is the manufacturing. You can see here on the left picture, it's an animation picture. The middle is the CT, and the right is also CT on this cross section of this component. You can see the whole magnetic field is inside. Many of you maybe you will think, where is the air gap? Because energy is always stored in the air gap. So you may afraid it will saturate too fast. No, no problem. We have here, because of iron powder, not sintered, air distributed by the distributed air gap. So the air gap is distributed, and you have complete enclosure. Magnetic field cannot break out. It's perfect for good EMI and extremely robust. If you do something by keyless entry or any RF designs in your car, you will need some ceramic inductor. So we decide to produce also ceramic inductor ACQ200 tested and can be achieved by plus minus 0.3 nanohenry, perfect machinery who can do that. And yeah, if you have any request of sample, just ask our colleagues. Not special EMI, but it could help and improve EMI. Colleagues from product management, they developed this pick and placeable SMD spacer. You have that in the tape and reel, and you can assemble it by pick and place machine. It's very simple to use it, and it's good for grounding, or you don't put hand work to place that spacer. I would use definitely this spacer instead of the plastic spacer, because they are much more robust, and of course you can improve your and speed up your process. If you need something by a screw, you can have that also with the M3 size. Not everything is possible by screw, but some of those they are possible to have also a screw, M3 screw, and you can use it also for fixing whatever. Another nice mechanical product is this contact finger. It's actually a copper beryllium gold plated, and it's also very good if you have contact between PCBs. Or I saw one of the customer, he did even avoid to use a connector, and he put that pick and place, of course, also by trace or by tape, and you can solder that on the PCB SMT. And he placed another stack PCB on the top, and he put even currents and grounding and datas just by putting these PCBs up above each other, and looks very cool and high reliable, very low impedance, excellent for contacting the, if you make PCBs by a ground edge, if you make that frame by a ground connection to the housing, it could be also clipped on it or soldered directly. It's perfect solution for that reason. What I can recommend more, if you want to read more about compassive components, or if you want to simulate them, we have this nice book, Theology of Magnetics, already the 5th edition, and also the LT Spice book is one of these very, very popular book if you want to make modeling or want to model your and simulate your PCB. I can really recommend that, and it's a good lecture for the coming Christmas time. So if you want to keep in touch with me, I have also a Twitter channel and LinkedIn. You can be with me and on YouTube if you want that. Just click on the link and you can see some nice videos which are provided by YouTube channel from Würth Elektronik. I show you then very short videos, how is a saturation current, nominal current, some ESD tests, and some funny stuff. Now I will open the chat and look what kind of question did you place there.
Yes, thank you, Laurent, for your interesting presentation. As you already mentioned, we would like to turn our attention now to your questions and wait a little second until some questions have come in. You can enter them in the chat function in your webinar control panel. But Laurent, as a first question, what would you say are recommended shielded inductor to be used as filter?
Thank you for this question. It's a good one. Well, if you use a shielded inductor for filtering, that's the question, right? If you want to put a shielded inductor for a filter, you have the advantage, okay, it's not a must to be shielded, but you have the advantage that the same size and the same package, you can do the same value with less number of turns. You can reach the same inductance value with less copper wire, so your DC resistance is lower. You have less DC losses, so the efficiency is good. This is the only one reason. It's not a must, but is welcome because you have less losses.
Okay, thanks, Laurent. Another question, Laurent, why is saturation current higher as nominal current?
Thank you for this question. Same. Why? Well, first of all, saturation current, there are no standard definition. The saturation current at Würth Elektronik, we define them according to the inductance value. It means if the inductance have 100% by 0 DC bias load and the inductors start to be DC bias loaded, after a while, on a certain point, the inductor starts to, this magnetic field, which is concentrate into the core, the core start to be saturated and then start to drop. The inductance start to drop, and then we define, like by the PD series or PTA, we say, as soon the inductor drop 10%, stop to use them. So the saturation current is defined only by the inductance drop. By the nominal current, we take care about the self-heating. Doesn't matter the inductance value, the self-heating. The self-heating is given by the DC resistance of the winding. So sometimes you will get an inductor which have a extremely low DC resistance, but because of the size, it could be that the saturation point is even before the nominal current. But the most time the inductor core is that big that normally the saturation point is much higher like the nominal current. So nominal current taking care only just by the temperature, no matter about the inductance, and saturation current, no matter about temperature, is taken care only by the inductance level. So I can see
Laurent.
here more question is coming. Just I have to expand my window. So another question I can see here. When choosing passive components, I try to choose a part, an assembly inductor, that's a footprint compatible with other manufacturer. Do you have a cross-reference list? Well, we are cooking also just by water. We don't use some special things. Many of our inductants are footprint compatible with many other market producers. So yeah, we don't have a special list, but if you look to the size of the component or you ask our sales guys, they know by heart which component can be switched over with other one. If you use a Würth Elektronik soldering pad, I can imagine that you will be able also to solder other one, but I will be happy if you still use Würth Elektronik component. Another question, whenever adapter pin is connected to the board, there is a spark. We have TVS and a common mode choke with the X cap and Y cap. And can we still ferrite bit in series for this kind of application? Okay, when you connect the connector to the board and you have a spark, it can be because of ESD. In this case, I would use a ESD suppressor for sure. If you have over voltage because of the long wires and induction, which can be stored in this long wire, and you have this discharge, for sure I will put a varistor. And the ferrite bead is actually um, after you put all this over voltage protection, you can put the ferrite bead, but this is here more for EMI, not for over voltage. So over voltage for spark is for me is for sure is over voltage protection. I would put first the ESD and then a varistor. Okay, is somehow to be powerful enough. The TVS, the powerful TVS, is also good, and a varistor is also very welcome. I had once I remember a problem similar in my um, designer time, and what I did done after the connector, I put a capacitor, um, um, bulk capacitor, something like 100 microfarad, to take over voltage first to charge him, to make this kind of load dump, to charge first the capacitor and then supply from the capacitor the energy to the electronic, because the wire was that long that already this over voltage could destroy the rest of the electronic. And the simplest, very easiest way was put a bulk capacitor there. Okay,
Thank you,
some other
Lauren.
question. I have another question
I
here. I see another one.
okay.
The last one. How about
Yes.
that one? Do you have components to protect 230 volts on board chargers? An example, 7 kilowatt single phase common mode choke, surge protection. Well, for 230 volts, we have a lot of different varistor which can be used. Of course, this is not a problem. Single phase common mode choke for 7 kilowatts. That could be a limit, but we have three phase for more kilowatts, but not single phase. For 7 kilowatts, it will be on the limit because they are already quite big common mode chokes. I have to check that on the website and on the catalog. I don't know that exactly if that's enough. I know for three phase we have them, but for single phase, I guess not. But of course, surge protection a lot, no problem. So
Okay.
how is
Thank
the
you,
time?
Lauren. I would say if there are any questions left, we will answer them via email afterwards. But for now, we are finished with this presentation. Thank you very much, Laurent, and thank you very much for your attention. And I hope you enjoyed the presentation. The next presentation is how cable and PCB ferrites can help to prevent EMC issues. And this presentation will start at 1 p.m. See you there and enjoy our digital days. Goodbye.
Bye.